Spend the lunchtime drinking instead. Right. I think this is the right time to start the first session, and the chairman for the first session is David Gross. Actually, take those off.
Right.
Oh, right. Also.
Give me the schedule. So on with the fun. Our first speaker is Steve Schenker, who will talk on inflation as a window into short distance physics.
Get that one.
I don't remember how the lights work.
Not gonna forget. Does the microphone work? Does the microphone work? How's that? No, it doesn't work? Zero level? Is that better?
Button your show.
How about that? This works. How's that? How's that? Yeah. That doesn't come off of my time. All right. As David announced, I'm going to talk about inflation as a window into short-distance physics. Most of what I'm going to describe is contained in papers with my collaborators, Nemanja Kaloper, Matthew Cleavon, Albion Lawrence, myself, and some in a paper that is, I guess, in the late stages of completion, contained with this group and Lenny Susskind as well. Well, it's a familiar lament to those of us in this room that experimental probes of string or M theory are hard to come by. Basic reason is that the string mass is a high mass, except perhaps for TeV strings, and we won't talk about that now because if that happy situation is true, we'll have so many ways of examining string theory we won't have to do the exotic kinds of things I'm talking about here. Well, the Big Bang indicates that we should expect very high energies in the early universe. And the earliest currently accessible signals of the early universe are in the cosmic microwave background. And they're usually thought of as arising from inflation. Now, inflation, just to remind you, is a period of exponential or more generally rapid expansion where you have roughly a de Sitter phase. The metric like this, a scale factor that grows exponential in time. And in the simplest models of inflation, you have a rate of exponential increase with an energy scale that's very high energy, 10 to the 13th or 10 to the 14th GeV. That's fixed by the experimental size of the cosmic microwave background fluctuations. And it's this very high energy that makes things so interesting, that drives our interest in this project. Okay? Of course, it's not necessary for H to be this high. There are other models of inflation, hybrid inflation and so on, where H can be as low as a TeV. But fortunately, H is measurable. Did this thing just die?
No, just put it down.
Do what?
So I'll just put the level down. It's still coming through. It's okay.
It's okay? All right. H is measurable, at least if H is a high energy, by measuring certain polarization characteristics of the cosmic microwave background. So we'll be able to see what it is. And of course, what you see in the cosmic microwave background are these famous kinds of curves that most of you are probably familiar with, where you measure spherical harmonic number on the sky and the amplitude of temperature. And it's the fact that this is not constant, these fluctuations off of a mean that are an indication of these fluctuations that we ascribe to inflation. What's interesting, first of all, is that these things seem to line up with inflation. These curves are inflation theories. And second, that these error bars are getting interestingly small. This data comes from a ground-based experiment called Boomerang. There are space-based experiments. There's a satellite called MAP in space now, about 1 million miles away. That's, I think, the first load of data is being analyzed as we speak. And these satellites are designed to measure this data with what's called accuracy at the cosmic variance limit. The accuracy controlled by the number of independent samples on the sky, which goes as 1 over the square root of twice the spherical harmonic number plus 1, the number of independent samples, which in this region is roughly about a 1% measurement. So this is going to be very highly quantitative, high precision data. And in fact will be as high precision as is possible to measure when it's obtained. So the combination of these reasonable assumptions about scales and current experiments leads to a situation with an immensely powerful 10 to the 14th GeV or so thermal accelerator, if you will, in the sky, and detectors that we can build or have built capable of 1% measurements that are online now. And this is just too juicy to pass up, okay? And so that really motivates us to try to see if there's something we can see in this. All right, well, a number of groups have studied the possible effects of new physics beyond ordinary inflationary physics, characterized by some heavy mass M, that could be the string mass or the Planck mass, on the cosmic microwave background. These are some of the early groups that worked in this field. These groups have used simple models to explore the qualitative nature of the effects that you might see. And they found effects, that is deviations from the naive prediction of inflation, that are proportional to the basic dimensionless ratio in the theory, this Hubble parameter over this heavy mass, either to the first power or to the second power. Okay, and this depends on certain choices we'll discuss at length later. To resolve open questions like which power it is, and to learn to calculate quantitatively, not just to get the qualitative dependence, in more realistic models, like if you take a real string compactification, calculate the real coefficient of these effects, our group formulated a systematic way to calculate. And the ideas of the systematic method are simple. We followed standard inflationary thinking and argued that rapid expansion effectively dilutes or erases or inflates away any reasonable excitation above the standard adiabatic ordinary vacuum you think of, let's say, in field theory. And I give an example here. And this idea is responsible for the predictivity of inflation. No matter what garbage you start with, very quickly after inflating it for a while, you end up with a quiescent vacuum state. And we use this genericity argument to justify using the standard adiabatic vacuum to calculate with. We'll have more to say about that in a while. The second idea is that this Hubble parameter, about 10 to the 14th GeV, is much less than M Planck or M string. So effective field theory descriptions are appropriate. Now, one might worry that we're studying strings in de Sitter space and we really don't understand, but if this theory is going to make any sense, we think it's plausible that with this larger separation of scales, factors of hundreds of thousands between the string scale and the relevant curvature and momentum scale, that effective field theory should be accurate. Third, the fluctuations of energy or temperature that one observes in the sky are roughly proportional to the fluctuations in the inflaton field, the scalar field that drives expansion. I won't explain it much more than that. Okay? Now, if you take a little patch of the inflating universe and imagine a piece of fluctuating inflaton, that's that squiggly little line in there, and then you imagine that patch inflating, this fluctuation grows, and it grows in amplitude according to some quantum law. Bigger, lower wavelength quantum fluctuations are typically bigger. But then, when the patch gets to be of order the Hubble scale, that is 1 over h in length, this wavelength continues to grow, but its amplitude freezes. I guess the slogan that goes along with this is that it drops out of causal contact. The peaks and valleys drop out of causal contact with each other. So there's no way it can really change in a coherent way. So you have this process where if you knew the size of this wave when the patch is Hubble size, you'll know its size forever. Well, not really forever. What happens is eventually inflation stops, these fluctuations re-enter the horizon and then they get recorded in the sky. But if you really want to know what the fluctuations in phi are when they get recorded on the sky, all you have to know is what they are when they're at the Hubble-sized patch. Okay? So that tells you, and this is a well-known idea, that to determine the size of these fluctuations squared, you just take the two-point function of the inflaton field evaluated at a momentum of order h. So that's a well-determined field theory calculation, because we can be an effective field theory at a momentum much less than any string scale or anything like that. So it's a rather generic kind of well-controlled calculation. And that will determine the answer. Well, so how do we determine how such a calculation is affected by heavy new physics? Well, we should write an effective field theory for phi, assuming we have new physics. Well, the interactions of the inflaton with itself are ignorable for reasons I won't go into. So we write an effective field theory for the scalar field, and it has a standard kinetic term. It can have a two-derivative term plus a term that goes like h squared over m squared, plus a four-derivative term over m squared, plus terms with more derivatives and more powers of inverse m. You might think of these as coming from an inflaton line with a loop of some heavy scalar field and integrating it out. And the only unknown thing here is the coefficients C1 and C2. The rest of the structure is determined just by symmetry and being in de Sitter space. So plugging into that effective Lagrangian, putting P equals H, you find the size of delta phi squared is just given by h squared over 2. That's the answer you get in pure inflation, plus a correction proportional to h squared over m squared, multiplied by these two pure numerical coefficients. So the temperature fluctuations, the things you observe on the sky, are the ordinary answer times a small correction that's h over m squared times a constant that's calculable. You calculate that constant by computing these leading irrelevant operators in whatever theory you're interested in. Now, if you have a theory you can control, like some M-theory compactification or weakly coupled string theory, you just work in flat space. You don't have to work in de Sitter space, and compute some propagator correction and compute the p to the fourth term. Okay, so this is a completely doable calculation, and in fact, in our first paper, this is a lot of what we did. So we now have an algorithm for computing these corrections, and one thing we see is that they go like h over m squared, essentially just following from the direct structure of this effective Lagrangian, with calculable coefficients that are just 2's and pi's and maybe coupling constants, depending on the theory. All right. There's been some disagreement about this line of argument. These authors in particular have argued that the first assumption we made may not be correct. In particular, they argued that not all excitations above the usual adiabatic vacuum inflate away, as I argued. They've argued that certain special excited states might just stay there as you inflate. Okay? And in fact, they discuss a family of de Sitter invariant states, or vacua, if you will, well-known ones, first discussed by Matola and by Allen, further discussed by Wald, and studied more recently in the context of de Sitter CFT by Busso, Maloney, and Strominger. And they've argued that these are plausible initial states for inflation, and once you start that way, they'll stay there. They won't go away. These vacua, it turns out, produce effects that go like h over m to the first power. Okay? And so the question is, are those viable physical initial conditions for inflation? Of course, the reason that this is an interesting argument is that if h over m is a small number, a small ratio, h over m is bigger than h over m squared. And it makes experiments more interesting. Well, our conclusion after looking into the situation is that these vacua are unphysical, and they're unacceptable candidates for inflating universe. And I can't give the full description of our argument. There's a whole series of objections that we have. But the basic objection is that these states, or vacua, as you will, as many people have shown before us, and we just basically built on their work, these vacua are full of high-energy quanta. Roughly, the ordinary adiabatic vacua is defined by a destruction operator on the vacuum is equal to 0. These other so-called alpha vacua are Bogolubov transforms of this vacua that are defined by a destruction operator both plus a coefficient times a creation operator acting on the alpha vacuum equals 0. And alpha is independent of K, so you have a mixing of creation and destruction to arbitrarily high K vector. So you've distorted the property of the vacuum to arbitrarily high momentum. So you've done something to very high momentum, very short distance. Okay? And so alpha differs from adiabatic at arbitrarily short distances. And it also turns out that this alpha vacuum is de Sitter invariant, so it does never inflate away. Nonetheless, it doesn't make physical sense. You can compute things like the expectation value of the stress tensor, which is given by this formula. What this formula tells you is that there's much more zero-point energy in the alpha vacuum. Since the zero-point energy is effectively divergent, and there's a larger coefficient in front of the alpha zero-point energy than before, there's vastly, a constant times infinity more than in the ordinary vacuum. But we know that the alpha vacuum has to join up to our ordinary world because inflation ends and we exit. And somehow we have to join up to our ordinary world, which certainly isn't in an alpha vacuum because you can check properties of our world that guarantee you that it's not in an alpha vacuum. An alpha vacuum would destroy everything we know about our world very quickly. Okay. So something had to happen to this enormous amount of extra energy. You can't just put in some subtraction, because when you exited from the alpha vacuum, the subtraction would be left there, and it would over-subtract, and this universe would curl up into a tiny ball. There's no sensible way of dealing with this huge excess in energy. Some people have tried to put a cutoff in the theory and say making it de Sitter invariant by injecting energy at some given energy scale. Well, that violates energy conservation, and this reservoir of energy you inject will have to gravitate itself, and so that's not satisfactory. So there's really no way around this problem. Well, I'm a little short of time, but let me just say that there's another way of thinking about this that's very attractive, where you think in terms of the static patch way of thinking about de Sitter space. If you think about a Hamiltonian, the standard adiabatic vacuum is the thermal state. And the stability under small perturbations is just the propensity of thermal states under small perturbations to thermalize. That's their stability. These highly excited alpha states, we don't know exactly what they are, but they're highly energetic. And it's almost certain what they do is these energetic states rapidly go out near the stretched horizon, near the edge of the static patch, where their effective energy is very high. They interact gravitationally strongly, even if the theory is essentially non-interacting. That means they thermalize rapidly, and that means they will relax back down to the thermal state. This implicitly assumes some kind of cutoff on the alpha vacuum given by the stretched horizon. But this thermalization is another indication of the fact that these alpha vacuum, appropriately understood, have to connect back to the adiabatic state. So again, our conclusion is that these states are not satisfactory, and the adiabatic vacuum is the only physically correct thing to use as the base point for inflation. Okay, well now, given that we have a satisfactory basis for calculation, we can actually do some of these calculations. So remember that these cosmic microwave background experiments seem to be able to measure, or will be able to measure to an accuracy of 10 to the minus 2, 1%. It turns out, I won't go into it, but you also need to be able to do this kind of measurement on tensor modes. That is, actually measure polarization of the cosmic microwave background, not just the amplitude that's being measured today. That's much more challenging and probably won't be accessible for a decade or so. Okay? The Hubble constant is around 10 to the 14th. So let's now do this estimate where the size of the error is, again, some numerical constant times h over m squared. I guess I've written it here. Well, twice is not so bad. Okay. Well, let's first imagine perturbative string theory. Okay, so you imagine having an inflaton and having a virtual loop of a string state. Okay? Well, the heavy mass m will then just be the string mass. You'll probably have a factor of the string coupling or squared to worry about. But roughly h over m squared will be 10 to the minus 11th, with maybe a factor of a tenth for the string coupling. This is far too small to see because 10 to the minus 11th is much smaller than 10 to the minus 2. So perturbative string theory is not going to make an observable deviation in the cosmic microwave background. It'll make an effect of what, a 100 billionth in relative size. Now you might say just do a really precise experiment, but remember you can't. Cosmic variance fundamentally limits the accuracy to which you can measure the cosmic microwave background, at least the photons. Well, clearly what you need to do is you need to imagine other kinds of string theories where this heavy scale is not so heavy. And, well, this gets into what I guess is currently called large extra dimensions, but in earlier days we thought about things like the Horzava-Witten type model, where you might imagine that the 11-dimensional Planck mass was not as high as you thought it was. There was a very interesting scenario that Witten advanced where the 11-dimensional Planck mass was around the grand unification scale of 5 times 10 to the 16th GeV. This model had the virtue of explaining precision grand unification and some kind of Calabi-Yau compactification. So we investigated this model in some detail. The heavy scale m is like 5 times 10 to the 16th. Calculating these numbers, you find a correction to the cosmic microwave background of about 10 to the minus 7th. Again, too small to see. But again, an improvement, a bigger effect because m is not as heavy. Well, then we really tried to push things and find some model that would produce an observable effect. And we found the main thing we had to abandon was perturbative grand unification. And we said, all right, imagine that we let the 11-dimensional Planck scale in an M-theory compactification go below the unification scale. We'll imagine that the precision unification is a little bit of a mirage and it gets fixed up in some way that we don't know. Then we can imagine a G2 compactification. G2 because it's better to have more large extra dimensions, as we've learned from extra dimensions. So we don't have to suppress the 11-dimensional Planck length so much. We don't have to make the large extra dimension so big to suppress the Planck length. And you can find not ruled out models with 11-dimensional Planck lengths on the order of 10 to the 14th. So capital M is about 10 to the 14th, about the same as h. And this suppression is about 10 to the minus 1. So easily visible if that model were true. I wouldn't bet my life on that model being true, but it has not been ruled out as of yet. Okay? So there is a region in parameter space that can be probed by the cosmic microwave background and not by other techniques. But the cosmic microwave background does not yet hit a sweet spot of string phenomenology. And the sweet spot that's especially interesting is the one that includes a precision coupling constant unification. Well, there is another experimental probe of inflation that is less talked about. It has not been actually made to work experimentally yet. And that's the direct detection of gravitational waves that were produced during inflation. Remember, these fluctuations during inflation were produced in the exponential expansion of a de Sitter region. You have Hawking-like radiation, and gravitons are produced just as well as anything else. And these directly produced gravitons are just free-floating, free-streaming in the universe, and are there for us to observe. Okay? We're free to observe these at whatever wavelength we choose, and so we could observe them at much less than cosmological wavelengths. So then there will be no cosmic variance constraint. There will be many patches of independent patches of the universe available, so there will be no fundamental statistical problem. There would be the slight problem that gravitons are much harder to measure or to detect than photons. They're so hard to detect that they have never been detected. Okay? But photons have been detected quite often. Okay? I think she's detecting some right now. But all right. Well, but on the other hand, people are not put off by this, and there are substantial projects underway to detect gravitons directly. And let me just tell you, sort of for entertainment value, about a very optimistic proposal that Cornish, Spergel, and Bennett floated recently called the GREAT Project. I can't even remember what it stands for. Gravitational radiation across the universe. But not as expensive as some things you've been involved in. Okay. It's a follow-up to LISA, which is a space-based, which is a follow-up itself to LIGO. It's a space-based detector of gravitational waves using space-based interferometers. And the geometry they're talking about is the modest geometry. This is a piece of the solar system. This looks like a real childish drawing, but it was done late at night, so forgive me. This is the sun. The green line is the Earth. This purple circular line is Neptune's orbit. There are other planets between these, but I've left them out. Okay. And in Neptune's orbit, there's a square array. Each little circle has 2 satellites in it. What do I have? Okay. There are 2 satellites in here. And they bounce laser beams between each other, measuring their position accurately. And they cross-correlate to kill noise and so on. It's good to be far away from the sun so the photons from the sun don't disturb the delicate accelerometers and a bunch of other stuff like that. Okay? The claim is, if I read the papers right, that you might get a sensitivity of about 10 to the minus 3 to 10 to the minus 4 of the strength of the inflationary gravitational radiation with such an array, which is pretty impressive. And just so to be optimistic, suppose this is a different signal, so we haven't calculated the numbers. Suppose I just use the naive estimate, h over m squared, no coefficient, is about 10 to the minus 4. That puts a scale m of about 10 to the 16th Jev, which is impressively close to, let's say, this Hrjava-Witten model scale. So we are within shouting distance of a really interesting region of parameter space. And just as an aside, this shows how important it is to get the difference between h over m squared and h over m straight. If we used h over m as of order 10 to the minus 4, we'd be able to explore m's of order 10 to the 18th, which is way deep into the interesting region. It's too bad that's not the way the world is. Okay. So this kind of direct detection of gravitational waves, which is far away, but might in fact be practical. It's certainly much more practical than building Planck energy accelerators, may actually get us close to quite phenomenologically interesting energies. And we'll just have to see how practical, in fact, it is. So I guess I'm supposed to conclude, and since I don't have any time, I'll conclude by saying that.
Okay. I think we have time for questions. I've been asked to warn the people in the aisles to get out of the aisle. You will be forcibly ejected.
Oh, I should leave this on.
Questions? Back there.
Steve, you had this argument where you wanted to eliminate this alpha vacuum by saying that the one-point function of the energy momentum tensor was divergent.
Yeah.
And you had, okay, that piece that involved the one-point function in the adiabatic vacuum,
Yeah.
I think that's also the static patch, right, at the horizon.
Right. But that will be, but that's the same vacuum as you have after the end of inflation. So you can, whatever is normalizing the cosmological constant now will fix that. The point is that the alpha vacuum has a big new source of energy.
Yes.
That's not fixed, that you need to fix.
Yeah, but you get a huge source already from the adiabatic vacuum.
I'm sorry?
But it's already divergent in the adiabatic vacuum, just at the horizon. So, I mean, I don't know how you're going to... You have a huge vacuum energy already.
Yeah,
because you have a
right.
divergent...
You have to assume something fixes the cosmological constant.
Okay. All right.
I agree with that.
I mean,
Okay.
From my point of view, you sound rather confident of calculating these corrections, but in fact, you're doing perturbation theory around a solution which doesn't exist. I mean, you need to rely on some phenomenon to generate the inflation in the first place, which you don't yet understand. And how do you know that the same phenomenon that provides the inflation doesn't affect the corrections?
Well, it's basically because the inflation is weak in the region we're calculating. We're assuming that h is small.
But you don't understand the origin of the inflation.
As long as h is small, it doesn't matter.
Well, if it's zero.
I beg your pardon?
What if it's zero? I mean, you're talking about perturbation theory around a background which you don't understand. I mean, you talk about corrections to inflation in M theory where there is no known way of getting inflation from M theory in the first place.
Yeah, okay. We should continue this privately. This is a...
Okay, last question. Andy's comment back there.
I'm sympathetic. Is it working? Yeah, I'm sympathetic with the idea that the alpha vacuum. I'm sympathetic with the idea that the alpha vacua are problematic in general. But my understanding was that if you take de Sitter space in global coordinates and then just stop the expansion in some global time, that there is a vacuum which has been called the in vacuum that goes over to the vacuum on the sphere. So that, in other words, what you're calling the adiabatic vacuum is not the one that matches onto the normal vacuum on the sphere with this kind of patching. So I don't think it's obvious that using these funny vacua will lead to problems of non-Minkowskian type behavior after the transition from inflation to a more normal universe has occurred.
Okay, I'll have to think about that. I don't know that. I don't know that examples. But do you know how the vacuum energies line up in that case?
It's just zero. There's no particles coming in. There's no particles during the inflation, and there's no during the de Sitter phase, and none after.
Well, okay. I guess we should. Yeah, I'd like to talk about that.
Okay, let's thank Steve again.